So, okay, switch back to English. I hope you can see the screen. And now we talk about collisions. This is a little bit of a difficult lecture to give because a lot of, I have to give you an idea about the connection with theory without doing too much theory. You have dedicated lectures for high energy physics theory and for theoretical physics that do this in an excellent fashion. However, it's impossible to do experimental particle physics without some theory understanding. The opposite is also true, by the way. So let's have some introduction. Layman thinks that I think every student of particle physics should know. What you see here is the particle content of the standard model. In fact, from these three generations of quarks, up, down, jump strange, top, bottom, and leptons, electron, electron neutrino, muon, muon neutrino, tau, tau neutrino, and the force particles, the gluon, the photon, the Z boson, and the W boson, as well as the Higgs boson. There's the standard model particles, but we need only very few to describe all processes that happen to us in everyday life, because the up and the down quark form the proton and the neutron. They are held together via the gluon to form these GeV scale bound states, and those then form the nuclei. The nuclei and the electron form the atoms, and we have the force of gravity that's not in the standard model, and we also don't know how to incorporate it. But besides that, all the forces we feel in everyday life, almost all of them, are mediated by the photon, which carries the electromagnetic force. And that's it. So we only need these very few particles. However, to describe the physics at colliders and to describe nature at the most fundamental level, all these particles are needed, and they are subject to symmetries and to concepts that are absolutely invisible in everyday life and are a miracle of nature, and it's a miracle that we can describe nature in our universe with so few concepts. So not a lot needs to be known, not a lot needs to be described everyday life, but there is a staggering level of detail, theoretical calculations, subtleties, and little tricks necessary to perform the calculations so that you can describe, for example, what happens at the plus and minus machines or at hadron machines. In colliders, we collide low mass elementary particles, for example, the electrons, maybe also the muon in the future, but mostly the electrons, and or nuclei. Could be hydrogen nucleus, that is the proton, could be heavy ions. And then we produce intermediate heavy particles, and then that cascade to lighter particles. The up and the down quark are light. The top quark is heavy. It has 173 GeV. That's more than, a proton has a little bit less than 1 GeV. So that's almost 200 times the mass of the proton. So we collide the light particles, the electrons or the proton constituents, the up and the down quark or the gluon, to produce the heavy particles, the top quark, the Higgs boson, the Z boson with 91 GeV, the W boson with 80 GeV. And then those cascade decay back to the lighter particles, which we record. many discoveries have been made with hadron colliders. That's because a hadron, think of a proton, consists of quarks, and those quarks and the gluon they carry in each collision a varying amount of the momentum of the mother particle, which is used in the collision, which means that every collision probes a different energy. You have two protons colliding with 2 times, say, 6.5 tera electron volts, but inside those protons you have constituents, and it's the constituents which react, but with a momentum transfer that is highly varying from collision to collision. And therefore, if you collide protons, you collide garbage cans, and therefore you test collisions at all energies that are kinematically accessible at the same time. And therefore, it's easier to make discoveries at the proton-proton machine. If you have E plus, E minus, then you have, you only have one beam energy, and that's your collision energy. There's nothing you can do about it except varying the beam energy. That takes a long time. But because you know the incident beam energy, you can control these collisions much more precisely. You do not know if a quark and an antiquark collide at the LHC or an up and a down quark. You do not know the incident energy. It's a random fraction of the energy of your proton. For E plus, E minus, that's different. You know it exactly. It's your beam energy. Hence, we call proton machines discovery machines. E plus, E minus machines, we call precision machines. Although it's not necessarily true. One can make discoveries at E plus, E minus machines. I list here now the most recent discoveries. No time to go through the details. Maybe let's start at the bottom. The tau lepton was discovered at SLAG with the Mach detector in mu events from E plus, E minus collisions. Which was the genuine signature of leptonically decaying tau leptons, because the tau can decay back not only to hadrons, can also decay to leptons. P quark was discovered at Fermilab in 1977 in a bound state U-epsilon, which has a dimuon resonance decay. The gluon was discovered at the Tasso experiment in 1979. It was difficult to discover because the gluon only interacts strongly. It was observed in E plus, E minus collisions by gluon radiation. Actually, I'll show it at the end of this lecture what it looked like. W and C boson were discovered in 83, 84 at the UA1, UA2 experiments at the SPS, which is now a pre-accelerator for the LHC, in proton-antiproton collisions. This was really the biggest confirmation that the standard model has something to do with reality. By now we know it describes reality to very high accuracy. Took 12 years to discover the top quark, because if you have the bottom quark, if you know the standard model and that these quarks come in generations, you know there must be something, there must be a top quark. It was, of course, not known what its mass was, and in the beginning people thought it's 10 GeV and kept looking. Eventually it was found at 173 GeV in 1995. That was when I was a teenager. I remember reading this in Spektrum der Wissenschaften. And now we do precision measurements of this particle, really high precision high precision measurements of properties of the top quark. And in 2012, I was a little bit old already, the Higgs boson was discovered at the LHC in proton-proton collisions. These are the most recent discoveries. I think the first three are really important to know. Now, let me give you an example what gets me at least excited about particle physics and what we are doing here. We talked about colliders. Now I want to do some physics. I give you an example from this summer. It's very recent. I've told you in the previous lecture that the Higgs boson couples to all the particles according to the mass of that particle. So it will couple to the top quark very strongly, indeed it does, and to the bottom quark less strongly. It couples to the electron very feebly. We can actually not, we have no hopes of observing Higgs to electron decay in the realistic future. But one can ask, Higgs to tau tau has been observed, by the way, by a colleague of mine at my institute. That's third generation fermions. But what about the second generation? So we cannot do the first generation. We can do Higgs to the third generation, but what about the second generation? Second generation is hopeful because we could probably observe the Higgs to mu in decay. What is needed to find the Higgs to mu decay? Look at this diagram. It's a Feynman diagram. It depicts what we think is happening at the LHC when we want to produce a Higgs decaying to a muon-antimuon pair in a collision of protons. For example, the proton could each collide via a gluon, produce a top quark. The top quark couples strongly to the Higgs boson. The Higgs boson decays to muons. The top quark almost always decays to W bosons and the B quark, and the W boson can decay, for example, to quarks, or it can decay to a lepton and a neutrino pair. So that's a very complicated decay chain, and you would start looking for the signs of two top quarks in this case, and an additional Higgs boson in that event, in the same event, decaying to two muons. I don't want to go into details. I want to tell you what part of the standard model are necessary for you to understand in order to understand this measurement. And it's an important measurement because it confirms the coupling of the Higgs boson to the second generation, and nobody's done that before. So what parts of the standard model are needed? First, we need to understand the strong interaction described by quantum chromodynamics, because it does describe the initial states, the bound states, the protons, and the probability to find that gluon in the proton. So QCD is needed, quantum chromodynamics. We need to understand how the gluon interacts with the top quark. That's also quantum chromodynamics. It's also the strong interaction, however, at the high momentum transfer. So we do what we call perturbative calculation. That's deep in theory world. I'm not going to discuss this in detail in the lecture. Axel in Graz, Tony Repan at the Technical University can do that much better. Then we need to know how the Higgs boson is supposed to couple to the top quark and to the muon. So we also need to know its mass. So we need to understand electroweak symmetry breaking, top Higgs coupling, top muon couplings. And then we need to talk about the final state particles here. We need to understand how the W boson decays into quark-antiquark pairs, how the top quark produces a B quark. We need to understand how these quarks behave once they are ejected from the hard scatter, that they hadronize, that they create showers of particles, that they first create showers of particles that then hadronize and finally decay. This is the low energy hadron physics regime of the standard model. Then we need the interaction of the muon with the detector. We need to understand how it produces electromagnetic radiation as its path is bent in the magnetic field. What happens when it hits the detector? The muon can hit or go close by a nucleus, so we also need to understand nuclear interaction with the detector material. So all in all, we need to know what happens when a heavy, and that's the muon now, a heavy charged particle goes through matter. The muon is heavy in detector physics. The muon is light in theoretical and in experimental physics. That's because it's a factor 200 heavier than the electron. Everybody considers the electron light. So we have to understand detector physics, which is a standard model at very low energies. And then we have to understand the peculiarities of how the B quarks behave in the collision and in the detector, because a B quark forms a B meson. A B meson has a finite lifetime, so it can travel millimeter to centimeter distances and cause displaced vertices. So all this has to be understood. That really takes a while and is a subject of this course. But I've talked about the work that we have to do. Let me show you the reward. First is something simple that I always have to explain in the beginning. When we talk about in high energy physics, when we talk about probabilities, we usually translate probabilities into units of standard deviation using a normal distribution. I put the sketch here so you can look it up. If we say something happens with a probability of less than or more than one sigma, we mean that it happens in 68% of the cases, and in 30% it does not. So a 3 sigma deviation is something that happens in less than 1% of the cases, 99.7. So with 3 sigma, we talk about observation. If the probability of an observation of a process to be wrong is less than 1 in 1,000, we say we have a 3 sigma confidence in our observation. 5 sigma is discovery. You see that the probability for a discovery to be wrong, at least in a statistical sense, it doesn't mean that nobody made a mistake, but in a statistical sense, it's in the ballpark of 10 to the minus 5. So this is just nomenclature. I think everybody has to know it. It's a simple translation of probabilities into more convenient numbers. Now let's look at the Higgs to mu result, and this is from 2020, from July this year. You see here the probability, we call it the local p-value, the probability of the Higgs to mu hypothesis being wrong, essentially, and it reaches 3 sigma here. In other words, we have observation of the Higgs boson became to 2 muons. You see lots of colored curves here. I'm not going to discuss it, of course, but these all come from different event categories. Here, the yellow one is the one that I had on the previous slides, 2 top quark and a Higgs boson, and there are other ones. So put all these are all measurements, put everything together, and only in 2020, a few months ago, we established with a confidence level of roughly 3 sigma that the Higgs boson couples to the 2nd generation of fermions in the standard model. To give you an idea what it looks experimentally, the Higgs boson is 125 GeV. Do you see this little bump here? This is the signal. This is what 3 sigma look like. Does not look like a lot. The null hypothesis is the green axis here, and the data points are indicated by this measurement. So in this little bump here, this is events that are consistent with a Higgs boson decaying to 2 muons. You do not even see this bump in the inclusive distribution. So one really needs advanced algorithms reconstruction algorithms, multivariate techniques at each step to dig it out. But I did not want to start today's lecture without telling you where we want to go. At the end, when we are done in February, I want you to have a much better idea about what's needed to achieve such a result. And also the other thing is particle physics is very much alive and kicking. We produce fundamental results every year. Good, there was a teaser. Now we start with the work, and the work needs prerequisites. First is strong interactions and the quark model. In the 60s, after World War II, first colliders reached energy to produce hadrons in the GeV regime. And at first, many particles were discovered and could not be systematically organized in any way. So there was a rich phenomenology, many particles and decays that were not understood. Murray Gell-Mann proposed then to organize all these new particles in spin 1/2 octets and spin 3/2 decuplets. He called this the eightfold way. He was the first to introduce the idea that protons and neutrons had constituents called quarks with fractional charges. So an up quark has a charge of +2/3, a down quark has a charge of -1/3. So if you put together two up quarks and a down quark, you get charge +1 proton. If you turn one of the up quarks into a down quark, you get charge 0 neutron. And because he exploited symmetries, he could then symmetry transform these quarks into new states and match those states with the experimentally observed hadrons and mesons. This worked very well. Few particles were missing, for example, the omega minus and the delta plus plus, and could then be searched for. And indeed, most of these predictions were successful, which gave some idea that really protons and neutrons do have, are not elementary, have fundamental constituents called the quarks. However, there was a great many of details were not known. For example, if a proton consists of quarks, you have two up quarks, they have the same electric charge, so they should repel each other. An object like the delta plus plus should not exist because it has constituents of only positive charge, so they should fly apart and not. What binds them together? And there was a second problem that the wave function of the proton must be totally antisymmetric, same as for the delta plus plus. So the delta plus plus was known to have spin 3/2. So that means if the quarks have spin half, all spins must point in the same direction. It consists only of up quarks. And these two facts together mean that the total wave function of the bound state is symmetric. But because it's spin 3/2, it must be antisymmetric. Otherwise, the spin statistic theorem was violated. So there was a quantum number missing in which the wave function of the delta plus plus, and in fact all the others, could be antisymmetric. And this quantum number is the color charge. So you have two problems. It's better than having one problem, because with two problems you can annihilate these problems and they go away and you're happy. And that's what happened here. Because the theory of the strong interaction describes how the quarks interact mediated by the gluon. The force that's mediated here is the strong force. The quarks carry a new quantum number. I mean, it's not new now, it was new then, which is the color charge. We call it blue, red, and green. Of course, these are just mathematical colors. It's nothing to do with the photon interaction and the visible light. This new color charge solves the problem of the symmetry of the wave function of the delta plus plus. It also helps explain, why the proton and the neutron can be stable and how these quarks with the same electric charge can be bound together. Mathematically, it's very difficult. It took decades to develop. It is a so-called non-abelian gauge theory. And the theory of the strong interaction, quantum chromodynamics, is part of the standard model. I discuss it because I need you to understand a central implication of the strong interaction that guides us through every single discussion of a physics result at a Hadron Collider. This central implication was already known early on. Nobel Prize for Toft, Wilczek, and Politzer. It's asymptotic freedom, and it means that the coupling constant, that is the strength of the strong interaction, decreases with energy. And that is because of quantum corrections. In a theory lecture, you will calculate these quantum corrections. We don't do that. There's no time for it, although it's nice. We need the experimental result and the theoretical result, which happen to perfectly agree. As a function of the energy, the strength of the strong interaction decreases. That means for very high energies, the coupling constant is much smaller than 1, and we can do perturbative calculations. That is, same as in quantum, you probably all know quantum mechanics. So you can solve the hydrogen atom, and then you put the hydrogen atom in an electric field, which is small. Then you perform perturbative calculations. We do the similar thing here. In the theoretical calculations, we collide initial state quarks, for example, or initial state protons for that matter. And we find that the theory predicts that if the energy is high, the coupling constant is small, and this perturbation series will converge. However, at low energies, this does not work. At low energies, the strong coupling constant goes through the roof. It diverges at 200 MeV roughly, where this coupling constant becomes 1, and you cannot perform any calculation. This means the following. Let's say we have a hadron collision, and a pair of quarks is produced that move from each other. I'm now discussing a very simplified classical picture, okay? This strong interaction means that there is a color flux tube between the two quarks that makes a constant potential. So if you move these quarks, if the quarks move further apart, you always need per unit distance of displacement, you need the same energy. The energy density in the flux tube is roughly 1 GeV per Fermi. But 1 GeV per Fermi is roughly the energy that's already, that's in a proton, because a proton is roughly a GeV and is a Fermi of has a diameter of a Fermi. In other words, a proton consists of quarks, and then with a GeV Fermi gluon field around it. And the same gluon field is created now until a distance of in the order of Fermi is reached, and then because of E equals mc squared, there's enough energy density to produce a meson, an anti-quark-quark pair. In other words, this color string, the field strength of the strong interaction, they snap and create a meson. And this continues to happen. Usually, it's difficult to describe this remotely. I hope you bear with me, but the time goes from top to bottom here. The quarks move apart. The field strength contains GeV per Fermi energy density, which creates new particles. And that continues to happen until finally so many particles have been created that all their energy are in the the typical energy transfer in these processes is all of them are in the single GeV regime. So we collide here with, for example, with hundreds of GeV because we collide with tera electron volts, and then this showering and hadronization process in the classical picture happen until we are left with hadrons that are colorless bound states, mesons and baryons. And this is a process that we must describe in effective models. And that's because at these low energies, when we are down here, when this process has happened, the coupling constant is at large values and we cannot do perturbative calculations. These non-perturbative aspects, these hadronization properties, cannot be derived from first principles. They have to be measured. This, unfortunately, is what makes physics at the Hadron Collider a little bit of a dirty subject. You start with a collision at a very high momentum transfer, you can nicely compute it, and then your nicely produced quarks that you would like to study, they create these flux tubes and field lines that produce mesons that give you a bunch of particles that you have to investigate. And from these particles, you can lose some. They can have different electric charges, so they spread out while they move through the detector, and you have to find them all back together. That's why physics at the Hadron Collider and this in hadron final states, let's put it this way, is difficult. Let me also, if you know theory, I don't know how much you've learned, but let me also highlight one critically important difference of the strong interaction, and it is the last thing I want to say before the break, because afterwards we start with studying the collisions. Think about gravity, Newton's theory. With Newton's theory, you can fly to the moon. You do not need general relativity. General relativity is a small correction to Newton's laws, to Newton's theory. In the solar system, we can only observe it in the rotation of the perihelion of Mercury, and a few smaller effects involving precision clocks and GPS devices. So you have Newton's theory, and then you have a more fundamental theory, general relativity, that's a small correction. The strong interaction is completely unlike this. It's the exact opposite. There we needed to understand the high energy behavior, but if we move down to low energies, to the classical limit that we've known before, the classical physics at the lower energies, then this theory collapses. The theory of strong interactions does not have a smooth classical limit. You can do electrodynamics classically. It's a correct theory, it's just not accurate. Once you look at precision measurements of electromagnetically interacting objects, you need quantum electrodynamics, and this quantum electrodynamics gives you small corrections. For the strong interaction, there is no classical theory that would have a smooth relation to the theory of strong interactions. This is because asymptotic freedom. Asymptotic freedom tells you that the energy, that the coupling constant is small at high energies, not at low energies. The classical world is to the left of this plot, where our perturbative description of the theory has collapsed. And that's why it took so long to understand, because it was unclear how would a new force with a coupling constant that's strong but that's smaller than 1, how can this explain these bound states? That's quantitatively extremely difficult to understand. It took a while to figure out this energy dependence of the strong coupling constant really plays the crucial role. So for once, in the description of the physics at the highest energies, we are in a regime where we are helped by a key concept of the strong interaction, because the higher we go in energy, the smaller the strong interaction becomes, and the better we have the perturbative control. That means we can calculate integrals and make predictions for the processes. Unfortunately, because once we have produced our interesting particles, as I explained at the beginning, they decay back to the lighter particles, and in decaying back, they go from the right of the plot to the left, and they leave the regime of validity of perturbative strong interaction, and we need to resort to empirical models of hadronization or this Gluon string that I described here a couple of minutes ago. Good. So I wanted to explain to you this key difference of the strong interaction with respect to all the other forces in the standard model. I stop now, we take a break, we reconvene it's 6:01. Let's reconvene 5 past. Oh, yeah, wait, I'm sorry. I need to bring back the schedule. When do we reconvene? I don't have it open. Let's reconvene at 1:45, okay? 1:45? Is everybody okay with that?
All right.
All right. So let's have some lunch and see you in a bit.